Now, what we're looking at today is how to select the correct motor for your project. So, if you're using a motor for your project, you want to move something. So, here's a selection of motors. They're low voltage, about 12, 6, can't remember what that is, maybe 10. It's a motor I got from Farnell. It's a motor with a gearbox on it that I got from Amazon, and this was on eBay. So you're going to want to move something. A few scenarios here. Supposing you have a conveyor belt and you have a box on it and you want to move the conveyor belt forward with a velocity, and you're turning the conveyor belt with a motor here. Power to do that is force by velocity. Another scenario here is a vehicle with wheels. Let's just say it's a cattle feeder. You want to move it along, drop the cattle feed. Again, you want to move along with some velocity V. Again, the power is force by velocity. Another scenario here could be this is some kind of gate that you want to open and close with a motor. In other words, turn the gate around. So your motor's here, your gate's here. It's got a center of gravity at M, mass M. Looking at it in plan view, again, you're going to turn the motor and move that mass with a velocity V. Here, it's a kind of a torque problem, so it's power is equal to torque by omega, but you can convert that into force by radius by velocity over radius. Now, no matter what your application, it's going to fall under two extremes. The two extremes being this one, where your motor acts like a hoist and lifts the mass through distance h and therefore a velocity v. Okay, what's the power required to do that? Where it's lifting it through gravity. Okay, that's the worst case scenario. The easiest scenario is that if you're moving the mass on a frictionless surface with a known velocity v average over a distance s, frictionless surface, your power is equal to force by velocity, your mass by acceleration by the average velocity. Now, unless you're trying to move something really, really fast, and for our applications in our projects, where we're probably moving something maybe at walking pace or something like that, your value of acceleration is going to be much, much less than g. So this one really is the worst case scenario. If you're moving something with no friction, and we'll come back, we'll continue on this, your acceleration of the body, which is causing the force, is going to be a very small, much, much smaller than g. For example, unless, say if it was a racing car, which you are not doing, and you were going from, sorry, that should read 0 to 150 kilometers per hour in time t equals 7.5 seconds, you'd have an acceleration of 5.5 meters per second squared, which is still way less than g. But I mean, that's just extreme, just to show you that we'd never be approaching those accelerations. Okay. Sliding with friction might be the case, but it's more accurate because this is an ideal situation. If you're sliding with friction surface, again, you want to cover distance time s in time t, so you have a v average. Again, your power is equal to force by velocity. In this case, though, you've got to overcome the friction force and add it to the accelerating force, which, as I say, isn't going to be much unless you're trying to move this at the speed of a race car. Multiplied by your v average. Now, your friction force will be the weight, in other words, multiplied by the friction coefficient. That gives you the friction force. Okay. Now, more realistically, you might want to be moving a mass with rollers, okay, or on wheels, because a conveyor belt is effectively moving the mass on some kind of rollers. In this case, you've got distance s, time t, v average is s over t. Your power is equal to force by velocity. Again, so that's going to be equal to your rolling resistance plus your accelerating force by v average. Again, I'm saying the acceleration force is not going to be much because our a value is going to be quite small. So your friction force is u subscript r multiplied by mg, and f subscript r is your rolling resistance. Now, I'm going to just pause for a while and show you the test setup I used for this experiment. Now, this is a test setup using the yellow motor. So you've got your, this is pretty rough and ready. You've got your yellow motor there. Okay, shaft going through here. This is kind of a simple jig I made up. And what I'm going to do is I'm going to turn on the motor and raise this weight here. So a bottle of water, which I can measure and weigh and calibrate exactly to weights and grams. I'm going to raise it through a height H. And therefore I can find out what the power is to do that. And the idea is to get what the power output of that small little motor is. I'm going to pause a sec. So if I turn on the motor, we can see that it raises up the mass. And it doesn't. Sorry about that. Pause. Okay, sorry about that. It wasn't really catching on the little shaft here. So, okay, you can see it raises up like that. Okay, so what I could do is measure the time taken and the height. mgh over t is the power required to do that. Now I'll show you the other setup. Okay, this is the test setup for sliding with friction. Now, what I've got is I've got the bottle of water, known mass, and I am allowing it to travel with friction in this manner like that. Okay, so this counterweight pulls it down, and like so. Now, the actual test was done a bit more sophisticated than that. Sorry about that. The actual test was a bit more sophisticated than that. The surface was much smoother, but in the same way, I could calculate what the speed of the bottle was, and I can also time it and get the speed. And then I worked out what the friction element of it was. So I was using the same mass, same time, or sorry, same distance. I can work out the power requirement for that. And then the rolling friction was just simply the same thing, except I had this mass of 300 grams and pulled that along and saw how long that took. So that's, I mean, it's pretty rough and ready test setup, but it works. Okay, you can still do the, you get the numbers you need. Okay, so when I did the test, what conclusions did I come up with? Okay, theoretically, I can work out what is the power requirement to move a mass of 300 grams over a distance of, it was 0.590 millimeters, just short of 0.590 millimeters, and what velocity and what power requirement that gives. Okay, so that the power requirement for a mass sliding with no friction over that length is 0.0001374. So 4 zeros, 0.0001374 watts. So I mean, very small, but they're very small masses. Okay, so that's kind of the zero, no friction, the smallest amount of power you're going to need. The hoist, the power to lift the same mass through the same distance is 0.055 watts. Okay, so significantly greater. I mean, this is your worst case scenario. This is almost doesn't require any energy whatsoever, or well, it does, but. So when I compared then this scenario, sorry, these four scenarios, so sliding with friction and rolling with friction, I found that with friction, the power requirement was 0.01077. Okay, so that's almost a fifth of the power requirement of the worst case scenario, the hoist. And then with the rolling friction, I found that the wattage requirement was 0.00469, which now is 1/10 of the power requirement of your worst case scenario. And notwithstanding that, the rolling even should be less of a power requirement than that, because this particular thing is not very sophisticated, as you see. And what happened was the wheels tended to slide along the surface, so it wasn't rolling nice and smoothly. So what I would expect the value for the wattage for, you know, a much smoother roller system to be way less than 1/10 of this system. Okay, so what does that tell us? Suppose your motor requirement is for a motor to move a mass of a certain weight at a certain velocity. If you do this calculation, you've got the worst case scenario, okay? But it gives you a ballpark figure, and then you know your wattage is never going to be that much, okay? In fact, it could be 1/10 of that, and there's a reason, and there's a reason that's good, even if it's 1/10 of that. So my advice is work out what the wattage required to lift the mass at that velocity, and you've got the maximum power you're ever going to need for your motor. Okay, so you've calculated your wattage based on this worst case scenario. So you get a number, okay? So you're looking to find a motor to do that. And this is where the problems arise. This motor got from Amazon Prime. The spec sheet, the description sheet, is very, very poor for this. And I couldn't find any, I kept searching, but I couldn't find any better. This tells me that the power output from that is 0.1 HP, which is equivalent to 75 watts. Now, I found that the maximum power I could get from that was 0.055 watts. Okay, so there's clearly some kind of error in that. 0.55 watts. Now, sometimes on motor spec sheets, they're giving you the power input, which is the volts by current. And if you go that way with this, it runs at between 3 and 6 volts. In fact, it doesn't. For me, it only runs at 5 volts, and the max I went up to 6 volts. I didn't want to exceed the 6 volts in case it did damage, but it certainly didn't run at 3 volts, and I needed to go up to 5 volts to run it. Again, be wary of what they say on these sheets. But even if it's running at 6 volts, and it's got the max current of 0.2 amps, with 6.2 doesn't come anywhere close to 75. I just think this is completely wrong. What's 6 by 0.2? It's, I don't know, I have my calculator here, but it's nowhere near to that. So this is not an accurate spec. Now, what is interesting about this is the max power I found I got out of it was by about 0.076 watts. So maybe there's some kind of error by 100 there, or 1,000 or something like that. Its torque is, the max torque I got out of was 0.0147 Newton meters, or 149 grams per centimeter, or 150 grams per centimeter. They're often spec'd this way. They tell you what the grams per centimeter is, as opposed to actually doing it in SI units. So you might find that for smaller ones. They're the tests I did on that. Okay, so that's minimal, as we say, and it's not correct. This is the Farnell motor. Farnell's a reliable supplier. I did a few tests on that, and I didn't have them done the proper rig, but at least this gives us a lot more information. It tells me, I should really show you that, guys. It tells me what the supply voltage, tells me what the power rating is. Now, in my test, it says the power rating is 5.6, and that is a correct electrical power rating based on the current and the voltages. So at least it's more accurate than this one, the other one. However, when I did the similar hoist test on that, I got about a 10% efficiency. In other words, the mechanical power was about 10% of that, much less. And that is, I believe, common for small motors. I read this on some website where they're doing tests on these, that to get an efficiency of 10% of the rated wattage is thereabouts. And that's why my point that this is kind of 10 times more than you actually need. Therefore, it might give you the wattage you might actually use. So if a cheap and cheerful motor like this is only giving you 10% output of what it specs, it say that if you find out what the worst case scenario is, at least you want a tenth of that. So I'd nearly double the wattage. So what I'm saying is, find out the worst case scenario, double the wattage, and then find a motor with that wattage. However, the wattages can be very misleading. As I say, this one, the wattage is a complete lie. This one, the wattage is correct in terms of electrical input, but not output, because the mechanical output is only 10% of that. And finally, this kind of cheap and cheerful one from eBay doesn't give any information whatsoever, really. It just tells me what the voltage you can run off, what the speed is. It doesn't tell me what the max current. It doesn't give any real information other than electrical information. And that's not worth pretty much a damn, to be perfectly honest with you. And I haven't done a similar test on this. I've done tests with this one, but not on what I would call my better rig setup. I know it looks pretty crude, but it was still more repeatable than others. So what do you do? Well, just to give you prices of these things. These were good, okay. I got 8 of these on Amazon, and I had the free post with Prime, and they were $11.30. Now this is going to do a fair bit for you. They're actually hobby motors for radio controlled cars. So this will move, this will easily move a mass of 300 grams or 500 grams even, because based on the test results there. So, I mean, you're not going to have, a little model motor car any more than 500 grams. So this is going to move, a 500 gram car on wheels. So it's good, and it's cheap and cheerful, and it's geared down to give a higher torque. This other one from Farnell is certainly more properly specified. Again, I need to do proper tests on this. This is Farnell, local supplier. It's not coming from China and cheapest chips. I got 2 of these for $15.50, including post. So the postage I think was a $5. And then these ones I got on eBay. I got 3 of them for €4.56. €4.56. I got 3 of them, but there was free post. And I mean, I haven't done a proper test on this, and I will do. And it is probably, if it's cheap as chips, it's probably no good. This one's good, I think. So in conclusion, what do? You want to get a motor for your project. You need to decide what the mass is, what you need to move, or estimate what the mass is, and then decide on what velocity it needs to move at. What's it moving at? Okay, that can be calculated either in turning velocity or omega and converted into V, or its linear velocity. But you need to know what speed you want to move it at, or its average speed. Okay, so that's going to give you power is equal to force by velocity. That's going to give you power. Pause there. So you need to know your mass and you need to know velocity. And if you do this calculation where your mg by the velocity, that's going to be the maximum wattage, I believe, for most applications you're going to need. So what I'm suggesting is you buy a motor that has, I would say, twice the wattage calculated here, because then you know it's going to be able to do that or that. Twice the wattage calculated here. I know I'm going overboard here. And get it from a reliable source, or make sure the motor has a proper spec sheet that gives you voltage, current, torque outputs, speeds, etc. The best type of motor actually is one which gives you a torque versus speed chart. So at different speeds, it's going to give different torques. So again, be wary. Do your research before you buy. And maybe if it's too cheap, maybe it is too cheap. Final word, good source of motors, believe it or not, is Car Scrapyard. The motor for the windscreen wiper is quite good. It runs at 12 volts, I think, and it's got a reasonably high torque and it'll do most jobs. And also another motor, if you get it, is motor from a golf trolley. So go into the shed and steal your dad's golf trolley and take the motor off it. Okay, that's all I have to say on that. Over and out. Bye.